Hi, everybody. Here I am at, oh, wait, I want to show, here I am. Hi, you can see me now. Here I am at Hogwarts, and I wanted to talk about something very wonderful and important, and that is the Modulo 7. Now, modular arithmetic, as you know, if you talk, in this example, I'm just talking about Mod 7, and Mod 7 means that all I look at is, because I'm only dealing with integers here, and it means I'm only looking at the remainder when I divide by 7. So 14 is the same thing as 0 in mod 7. And, 27 is the same thing as 6 modulo 7, and so on and so forth. So that's how that works. Now, there are many there are many. I'm sure you've seen this at some point in your life. Modular arithmetic. Sometimes they call it clock arithmetic because it's kind of like like it just repeats itself in a clock, and because the hands of the clock is kind of like mod 12. And 12 could be like a 0 really. Anyway, so we're looking though at this aspect in terms of it being a group. So now we don't have now there are 7 digits in mod 12, 7 elements, 7 mod 12 numbers, 0, 1, 2, 5, 6. Right now, I want to look at the idea of mod 7 being a multiplicative group. So I'm going to take out the 0, which is fine. We're just looking at a subset of the numbers mod 12. Because zero kind of messes things up. Um, Not the least of which is the fact that a group has to have inverses and 0 doesn't have an inverse. Because anything you multiply by 0, you just get 0. And there's nothing you can multiply by 0 and then get the identity element. But it does have an identity element, and that would be 1. Let's fill this table out. Let's just do some multiplication. So obviously 1 is, just like in regular numbers, 1 is the identity. So 1 times 1 is 1, and 1 times 2 is 2, and 3, and 4, and 5, and 6. I don't want that. I want this to be centered here. Much better. And of course I can go this way. Now, 2 times 2 is 4. Isn't that great? You had to take an advanced math course in college to learn that 2 times 2 is 4, but it is. 2 times 3 is 6. That's nice. Now, 2 times 4, we all know, is 8. But in the world of mod 7, 8, there is no 8, but 8 has a remainder of 1 if I divide it by 7. So really, 8 is equivalent to 1 in the world of mod 7. 2 times 5 is 10, which has a remainder of 3, so that's equivalent to 3. 2 times 6 is 12, which is the remainder of 5 when I divide by 7. And there you go. Now I'm just going to cheat and copy whatever the last column becomes my next row. The last row is going to be my next column, 6, 1, 3, 5. Now, 3 times 3 is 9, but 9 has a remainder of 2 when I divide by 7. 3 times 4 is 3 times 4 is 12. That has a remainder of 5. 3 times 5 is 15, which has a remainder of 1. And 3 times 6 is 18. 18 has a remainder of 4. And there we go. And that means here I can go 5, 1, 4. There you go. Now, 4 times 4 is 16. 16 has a remainder of 2 when I divide by 7. 4 times 5 is 20, which has a remainder of 6 when I divide by 7. And 4 times 6 is 24, which has a remainder of 3. Isn't that nice? Now let's put a 6 and a 3, and we're rocking and rolling here. Let's see, 5 times 5 is 25. 25 is a remainder of 4. And 5 times 6 is 30, which is a remainder of 2. Because 28, right, the remainder 2. And again, now there's a symmetry here because multiplication is commutative. I mean, in other words, it inherits mod 7 inherits the commutativity that multiplication has. And finally, 6 times 6 is 36, which is mod 1. So first thing if we want to show this as a group, Well, we want to show that there's an identity element, but that's pretty simple because one is the identity element, and it's not doesn't take two. You don't have to be a rocket scientist to see that, or a brain surgeon, or whatever you want to call it. And that's one thing. The other thing is that um, what was the other thing? The other thing is that inverses. Well, you could see that there's inverses here because, well, one has an inverse, right? Because 1 times 1. 2 has an inverse. In other words, what I'm doing here is I'm looking for all the ones in the yellow field. 2 has an inverse because there's a 1 there, so 2 times 4 is 1. 3 has an inverse because of that 1. 3 times 5 it gives me the 1. 4 has an inverse because the fact that there's a 1. As long as there's a 1 in that row or column, that means that there's an inverse. 5 has an inverse, and really the fact that every row and column has an inverse is but if you notice this table, the yellow part of it is Sudoku-esque, meaning to say, Sudoku, you never have in any row or column, you don't have any numbers repeated. So it has that like sort of Sudoku-ish, and that's again, it's not a coincidence, there's reasons for that, and so on and so forth. Anyways, so we have here, so we have an identity, we have inverses. Now we'd have to show associativity. I skipped that one. That's usually first, but I skipped that. It kind of inherits associativity from regular addition, but I just want to show you. Let's see how we could show this a little bit. Okay, so let's say I have a number here. A typical number in mod 7 is going to be 7n plus. I'm just going to say a, where a is some digit. A is between. Well, I'll get that in a second. And I don't know if I might be going through more than I even need to. So A, B, and C are integers that are greater than or equal to 0, less than 7. So if I'm trying to show associativity here. So 7n plus, so a mod 7 number, any integer is 7n plus a, 7m plus b, and 7k plus c. And no matter whether I have the parentheses here or the parentheses there, when I multiply this out, I'm just going to get some big mess. But every term is going to have a 7 in it, at least one factor of 7 in it. Some are going to have more than one factor of 7. Plus, the only term that is not going to have a factor of 7 is a times b times c. So this is going to be 7 times some big number plus ABC, and that size is going to be 7 times the same big number plus ABC. So really, they're both just ABC. So all that matters really is the ABC part. The rest of it is irrelevant. That's why, by the way, if I multiply let's say 93, times 93 times times 40, I don't know. So 93 times 40, so 93 is 7 times 13, plus 2, and 40 is 7 times 5. 7 times 5 plus 5. So really, this is just going to equal, again, 7 times some big giant number W. I think W stands for wonky, plus 2 times 5. So, so really all that matters, and that's and in mod 7, which is 3, mod 7. because 2 times 5 is 10, and 10 is the same thing as 3 minus 7. So all that really matters is the remainder, because everything else is going to have 7s in it, and it's all going to disappear. And that's kind of really this. So basically, you have to show that that's, and going back to the original thing, to show that this is a group, we want to show the 3 properties. We want to show associativity and all everything that's from the definition of a group. And just to refresh your memory, what's the definition of a group? Just put that right here. A group consists of a non-empty set G. Yes, it's definitely non-empty. And a binary operation star, in this case, stars multiplication, satisfying associativity, identity element, and inverses. As long as I show these things, I'm in business. And that is my group. And that is how you would show that that is a group, not all the integers mod 7, but just the 1, 2, 3, 4, 5, 6. I took a subset of all the different integers, because I'm not, again, I don't want 0, because 0 is going to be a big pain. Because 0 won't have there won't be any. If I would have put 0 into the table, there'd be no inverses. And that, my friend, is the story. That's how the professionals do it. So that's it for this video. We'll see you guys next time, and it has been wonderful. Bye. Bye, everybody. I'll give you regards to Dumbledore.